So we'll now continue with the lean session with Jeremy Abigat.
Okay. Okay, so I'm sharing my screen. So any of you can't see my screen, let me know.
Yeah.
So I'm not displaying it. It's just my blank screen. Yeah. So one of the things I want to do is I want to start by convincing you that you don't really need me to give a tutorial, in the sense that I want to show you some resources online for you learning to use Lean. And really the way to use Lean is just to muck around and experiment and try it. It is useful to have somebody knowledgeable around to kind of look over your shoulder and, provide advice and suggestions and, provide, answer questions when you get frustrated or stuck. So what I will try to do is talk for about an hour and then just kind of stop and let you play with me and then just be on hand to help you. But yeah, as far as learning Lean, so the first thing you should make sure you know how to find is the Lean community web pages, because there's a lot of good stuff there. And so if you haven't poked around there or nosed around, you should give it a try sometime. There you'll find so information on how to install Lean and get started, and it suggests using mathematics and Lean. So we'll look at mathematics and Lean in just a second. You will also find here learning resources, and a very good one is if you've never seen Lean, if you're really totally new to the game, the natural number game is really great. It's kind of like it has a video game vibe. You go through levels and you prove theorems and advance. And so if you're really just totally new to this and want to get started, I encourage you to try out the natural number game. It'll give you a feel for a feel for Lean, and then you get started. And so where was I? Oh. I hate using Zoom because the bar gets in the way. Another thing to show you is this link on the side to API documentation. It kind of buries the lead. I mean, the API documentation is where you can sort of browse MathLib, and so this is always a fun thing to do. You can kind of nose around and see the kinds of things in the number theory folder, and just kind of click on files and see theorems and so on. And the last thing I want to show you is also, if you go to the Lean community pages, you can also find a link to the Zulip chat, and I recommend going online to checking out these. So you can't, when you sign up, you have to give a name and an email address. You can't be entirely anonymous, but there are like 10,000 people kind of signed up, so you really can be almost anonymous and sit and just watch posts go by. But it is a very friendly place, and there are streams you can just sort of follow the news, but there are places where you can kind of introduce yourself. Where is it? New members. If you go to the new members stream, you can see that somebody's just kind of you can go here and introduce yourself, and people will give you a friendly wave emoji and so on. So if you're just getting started, the algorithm is go to Lean community pages, look around, play the natural number game, sign up for Zulip. But then a good place to start is mathematics and Lean. So if you follow the instructions to install mathematics and Lean and get it up and running, then you should be looking at something like this. You have mathematics and Lean and a folder called MIL, which, let me back up. So you can find, So if you just search for mathematics and Lean, you can find the textbook online. So it's HTML. And one of the things that the introduction chapter will do is tell you how to get started and how to install it, and get it up and running. And the idea is there's an associated repository that has files with all the examples and exercises and solutions. And so if you fetch that, you basically have this. And so, for example, in the basics section, you can go to the first section, which is calculating in lean. And the way to use it is, the idea is you should be reading the textbook and experimenting with the, with lean at the same time. So if you do Control-Shift-P and start typing lean4:docs show documentation resources. So again, this is in the textbook, it'll tell you this, but you should be able to choose mathematics and lean. And there, so in VS Code, you sort of have a copy, you have a copy of the book. Let's see, let me see if I can set things up. So let me go here and toggle the info view. So, if you can get things set up right, what you can do is something like this. You just start reading the first chapter, and it'll tell you about the syntax in lean and how to do calculations. There will be an example. In the repository, you should be able to find the example and step through it. So if you then switch to the info view, you can kind of step through the example and see things change as you go. And then, it'll get to the point where, there's text, and then they'll say, here are some examples for you to try. And then if you go over, to the the associated file, you'll find, the examples there ready to go. Actually, we do suggest, I should have said this, we do suggest, instead of working in the main MIL folder, just making a copy of it and working in the copy. And what that means you can do is, you can work through exercises as you go and change it, but you still have a copy of the original files around. It also means that if, a month from now, the textbook has been updated, the repository has been updated, you want to pull the newest version, it won't conflict with the changes you've made. So there's really no harm in working in the main folder, but to avoid conflicts later on, you can just make a copy of the folder. Yeah, so that's it. So the textbook is still a work in progress, and it really needs more work and so on. But it seems to work pretty well as a tutorial for learning the basics of lean. And so what I'll do now is just give you a tour of lean. But then when we're done, I encourage you just to go to Mathematics and Lean and poke around and try some exercises. Oh, and there are solutions, right? So if you get frustrated, you can find the corresponding solutions files and so on. If you're stuck on something, you can get.
This is super helpful. There are two things. I didn't know there were solutions, but also it used to be like on the Lean 3.1 that you could click on in the book and it sort of brought up the example. Now it's separate.
Yeah, we did. Yeah, we sort of made that change. Because there are advantages to each, but it's kind of nice having a whole file in front of you so you can scroll around and jump around. Okay, so what I'm going to do now is work in a demo file that I've prepared, and I'll use that to give this tutorial. Yeah, and so there is, if you are connected to the Zulip, there is a copy of this file on Zulip that if you want, you could download it and drop it into the repository and follow along and type things while I'm doing it. But there's no need if you want to just kind of sit back and just watch me do it. That's fine. There's no harm in doing that. Okay, so before, that was a long prolegomena, but before I get started for real, are there any questions? Oh, good. Once you get me started, I can just go on and talk and talk and talk and talk. So please don't hesitate to interrupt me, throw something at me. Yeah. Okay. So let's talk about Lean and what it does. So a thing to know about Lean's foundation is that in that foundation, there's only one syntactic category of objects. So everything you type is an expression. And the other thing to know is that every expression has an associated type. If you apply the first axiom to the second axiom, that you'll conclude that every type is also an expression. But that's it. So there are expressions, and some expressions are types, and every expression has a type. So just to give you some examples. So yeah, so at the core, there are really two things that Lean can do. One is it can parse expressions, check that they're well formed, either figure out what type they have or check that they have a given type. And as I've described it, that sounds like multiple things. There's inferring the type or checking that it has a type. But this is all part and parcel of the same thing. So parsing involves inferring types and checking types simultaneously. So I'm grouping that together. And there's a command you can give Lean called check that just says, check this expression. So check the expression nat. And Lean in the info window is telling you that nat is a type. Okay, so that's what the colon means. The amount of information flowing back and forth is kind of daunting. I mean, if you hover over the the squiggly mark, it'll pop up the information that's associated with that. There's the information window here. As you hover over things, you'll find you can click on things, and you can control click to jump to definitions in the files, and there are there's documentation. So there's a lot of information flowing back and forth. So if I check nat, it says it's the type. So in MATLAB, we define Blackboard bold notation Unicode. So if you type Blackboard bold N, it'll tell you that's a type. That's just notation for the natural numbers. And if you kind of hover over it, it'll tell you it's the type of natural numbers. It'll give you documentation. It should also tell you how to type the Blackboard bold. You type it with \n, for example. We'll do it, or \man. So it gives you all of those options. And as I said, if I control click, on that, it'll actually jump to the definition, the library, and so on. So there's natural numbers, there's integers, there's real numbers, Blackboard bold real numbers. If I check nat to nat, so this is the type of functions for natural numbers. So it's the type of data type of functions to take a natural number as input and gives you a natural number as output. Let me stick with the Blackboard bold. This is the Cartesian product, so the type of pairs of natural numbers. There's also things like things that you would find in any programming language. There's, for example, the types of lists of natural numbers and so on. So each of these expressions you see has type. And so think of that as saying that these are all data types. And we can also type expressions that are objects of those data types. So if I type check 2 + 2, it tells me that 2 + 2 is a natural number. You can also tell Lean that no, you want the real number version, and it said, oh, okay, 2 + 2 is a real number. So putting parentheses, putting this annotation around it is telling Lean, confirm that 2 + 2 is a real number. But what's going on is notation like 2 and plus is overloaded. So in the formal expressions underneath, there's a lot more information. And so this tells Lean to parse the expression specifically, do your best, figure out how to parse this as a real number and fill in the information. And so Lean does that and says, okay, it's a real number. Let's see. So by default, if you just type in a numeral, it assumes it's an actual number. But so here, the tuple 2, 3 is a pair of natural numbers. 2, 3, 4 is iterated pairs. It's a triple of natural numbers. You can do, the function which adds x to x + 2. You can take the real version if you prefer. Right? So yeah, so read this as the function which maps x to x + 2. So previous versions of Lean use lambda, the lambda notation. We write lambda x comma x plus 2, so Church's lambda notation. But lean 4 switched to this. And then mathematicians, kind of don't like that arrow. Mathematicians are finicky about notation. And so you can also use equivalently the maps notation, the maps to arrow. And Patrick Messot was adamant from the beginning. He's like, okay, we need to have this arrow in that. So yeah, people are very particular about their notation. And so so if you just go through the types, 2 plus 2 is a natural number. This thing is a real number. Here's a tuple. Here's a function from real numbers to real numbers. Okay. So again, every expression has a type, and here the check function parses it and tells you the type. So one thing that's interesting about lean is, so these are, you can think of, data types and objects, but you can also write down assertions, right? So I can, write down that 2 plus 2 is equal to 4. And if you ask lean what type of object that is, lean tells you that that's a prop. It's a proposition. It's a statement. And propositions, think of just mathematical propositions, things that can be true or false. So, I mean, they can be false. I mean, you can write down, 2 plus 2 equals 5, and there's a false proposition. And so, and you can write down, for example, there are infinitely many primes. You can say for all n in the natural numbers, there exists an m greater than n such that, prime m, right? So this is the statement that for every natural number n, there is an m bigger than n such that n is prime. So this is one way of formulating the statement that there are infinitely many primes. And again, lean tells you that that is just a proposition. And so far we've seen 3 types of expressions. There are data types. They have type. There are objects of those data types. There are propositions. And the fourth category of expressions in lean are proofs. So a proof of 2 plus 2 equals 4 in lean is represented as an expression with that type. Okay, so when lean checking that an expression has that type is checking that the expression is a well-formed proof of that type. And in this particular case, 2 plus 2 equals 4, has a particularly simple proof. So RFL is short for reflexivity. It's just the axiom, or it's the axiom of equality, that for every x is equal to x. And what's going on here is that this forces lean to actually unpack the definitions of 2 and plus and reduce and simplify and check that just by unfolding definitions, you can verify that. So most theorems are not that easy to prove. Again, what's going on is that, so this axiom with some, so this expression, RFL, is parsed with additional information in the full expression in such a way that makes it a proof that 2 plus 2 is equal to 4. Right. And so if we can, write down an expression that has this type, then we've proved in lean that there are infinitely many primes. And it's almost as easy to write down, Fermat's last theorem or the twin primes conjecture or the Goldbach conjecture. And again, producing a well-formed expression that has that type means that you prove that theorem. And that's that's the game. So in lean, whenever you define an object like foo, you're basically taking the identifier foo and associating it to that expression, and it gets stored in memory. That foo is associated with 2. And if I type theorem, bar is the theorem that foo, is equal to 2. And again, lean can prove that just by unfolding the definition. But so lean takes this expression, of this data type and associates it with the identifier bar and stores it in memory. And so, if you're proving theorems in lean, you're just writing down expressions and associating with identifiers and putting them into the environment, into the memory. And if you build on top of MathLib, you've got all the things in MathLib, in the environment to work with. But that's what you're doing. You're just writing down expressions, checking the types.
You said this, but in the example of the infinite number of primes,
Yeah.
the check returns what, prop?
So it says it's just a proposition.
But what's the vernacular when one comes up with the proof of that statement is it's not type prop, there's lots of things type prop.
So the
what's
proof
the word
will have this type. So prop is treated as a type, right? So for example, if I ask Lean to check bar, it says bar is a proof that foo is equal to 2.
Oh,
Okay, so having the type means being a proof.
but what did the check return? I missed it when you checked.
So check bar says, I'm asking Lean, tell me the data type of bar.
I see.
And it says, oh, bar is the theorem that foo is equal to 2.
I see. The statement is of type prop, but the proof is of the type of the statement.
You want to say something about the Curry-Howard?
Yeah, no, I understand it.
That's it. Now you know what the Curry-Howard isomorphism is.
Some people can
So
look it up,
the way proofs are encoded are objects of the associated type. And the rules of the logic are set up in such a way that constructing an expression that has the type is tantamount to having a proof of that type.
And what about the hierarchy of the types? If you do like check type,
Yeah, so I was trying to, let's save that to the discussion, but yeah, so if you check type, what type of object does type have? Well, it has type 1, and if you check type 1, it'll tell you it has type 2. What's going on is that there's a universe of types. Most data types comfortably live in the universe of type, right? Just the first universe. But for example, you might want to define a group to be, to consist of a carrier, which is an arbitrary type, together with a multiplication and a unit and an inverse, satisfying the axioms. And then group becomes type, but the type of group is going to be, too big to be an ordinary type because the carrier can be an arbitrary type. So you get to paradoxes of size and so on. And so there are increasingly large universes of types. Yeah, we can talk more about that later.
What's the largest number in MathLib?
So in the library currently, the largest one is 4. Typically, most things are in type 1. If you have a class of groups, rings, fields, those are type 2. So those are, most of them are type 0. Groups, rings, fields, type 1. If you wanted the category of all groups, that would be type 2. And beyond that, it doesn't come up.
Somebody was 4.
It comes, so Mario is talking about figuring out how you can sort of get it down. So there's some things that just by kind of coding artifacts, you get these extra generality that aren't really used in any essential way. But still having this universe of types, there's a lot of cleverness going on that kind of keeps it kind of invisible to you, so that it's it's just kind of a useful abstraction of generality. Yeah, just to come up with maybe a slightly more interesting definition. So if I define a function baz to be x to be x plus 3. So this is the same as writing, defining baz to be the function which maps x to x plus 3. So this is just more programming language notation. But I can, prove a theorem, called baz, which says that, for every natural number x, let's say baz of x should be equal to x plus 6. And the proof, so this can be done automatically just by unfolding, and the simplifier is smart enough to do the computations.
Sorry.
Okay. Yeah, so far so good. Yeah, I said that there were 2 things that that Lean can do. So the first one is writing down expressions and then checking that they're well formed. And we've seen that in a sense, this is really all of mathematics, right? You're proving theorems. It's just a matter of writing down things and writing proofs. The other thing is that you can evaluate expressions. So most of Lean, well, Lean's core foundation has a computational interpretation. So, you can also say, evaluate, 2 plus 2. And Lean will calculate that as equal to 4, or you can give it kind of bigger numbers, and we'll do calculations. What is going on? Function expected at. Interesting. I don't know just what happened. Okay. Anyhow, so Lean can evaluate expressions. So for example, if we were to take a moment and define the factorial function, you can then just evaluate the factorial function. And so that makes Lean a programming language. And so, if the first thing is just checking types, I said that's all of mathematics. Evaluating expressions is basically all of computer science, right? You write programs and you run them, right? And Lean can do that. But I just want to mention this. So we're going to be focused on the proving side, which is really, writing down things and proving things about them. But I just want to mention, just an aside, that that one of my favorite things about Lean is the way it brings together kind of the proving and the computation. So first of all, as a programming language, Lean is actually quite a good one and a very interesting one. In fact, Lean itself is written in Lean. Most of Lean itself is written in Lean. So the things that are parsing all these expressions and checking their types and and writing them to disk and loading them and providing information for the editor to display and so on. All of that is written in Lean itself, which is remarkable. But so having that all in the same language means that in Lean you can write programs and prove things about them. Also turning it around, you can sort of use Lean as a programming language to help you write proofs. And when you do that, you're stepping outside the formal foundation, but within the same file that you're proving things, you can write code that gives you automation, or gives you tools to help prove things. And so this interaction between computation and mathematics, I think is really exciting and pleasant. Okay, so far so good.
So is it generally true that if you prove that something exists, that it could produce a program, an inefficient program, that you've got a program to prove to?
So by default, well, okay, so let's see. So I could write down a statement of the twin primes conjecture and say, if twin primes conjecture, then 0 else 1. And if you try to evaluate that, Lean will tell you that it's not computable. So Lean knows what's computable and what isn't. By default, everything you write down is computable. If you try to write down a definition that isn't, Lean will give you a warning. And either you have to write non-computable definition, or you have to say non-computable section at the top of your file and just, you're saying leave me alone. So by default, you're working in the core logic, you're computable.
And that is like the usual kind of logic idea of computable. There's something that,
Yeah, it is both being the constructive fragment of the logic, and it also means that Lean can generate bytecode.
but there
And
are
it does
lots of
both at the
theorems
same
in
time.
like real analysis where it wouldn't be.
So
obvious
once
how
you,
to-
let's even try it. So if you, so you'll notice that if you say, let's see, if I try to say eval, so let's say, 2 is a real number, and I say 2. So I think, so I'm not even sure what's going on. If I try to evaluate the real number 2, it seems to know that it's the Cauchy sequence 2, 2, 2, 2, 2. I don't know
Why not?
how Lean is, but on the other hand, if I do say division, once you get to division, Lean knows that this is not computable. And if I said,
What was it that was not computable?
2 divided by 5 in the real numbers. Okay, because division for the real numbers, if you're to define it with like Cauchy sequences and equivalence classes of Cauchy sequences, to actually write down the definition, you have to know whether your denominator is 0 or not. And given a Cauchy sequence, you can't computably tell whether it's 0 or not. Right? So once you start developing real numbers, once you get to any, that's just non-computable. And so Lean knows it, and once you deal with the reals, you just so if I define foo to be that, it says I can't compile it, I can't generate byte code because the definition of division for real numbers is just not computable. But if I say non-computable def, or even better, let's do it this way. You say saying non-computable. I mean, mathematicians like to do this. You say non-computable section. It's basically looking Lean straight in the eye, saying, "I don't care. I'm not going to be computable." And then Lean doesn't bother you. Doesn't bother you about it. But I mean, that's a nice thing when you can define mathematical. You can define computable. You can write programs. You can define abstract mathematical objects. You can execute the programs.
And then is this
things.
classical logic a further addition, or is that already counted in this, like excluded middle?
So you can use, well, so what's the question? So the core logic doesn't include the law of the excluded middle, but almost everything that's done in Mathlib makes free use of the law of the excluded middle.
Right.
A nice thing is you can write programs and then use abstract classical mathematics to reason about them. Again, Lean does a very good job of keeping track of what it can compute and what it can't. And when it can't compute something, it generates the byte code right away. Okay.
So Lean computes integers and
integers are computable. Yeah.
and then rational numbers,
Yeah, rationals and
but not real numbers.
but not real numbers. Yep.
Does that mean that when someone wrote, presumably what it means to do the division in the real numbers, they had a tag that was non-computable, or Lean learned that, or I mean, how did it
And so basically, if they wrote a definition, Lean would give a warning, and they'd have to say non-computable definition or non-computable section.
Because
Right?
it could
I
tell
mean,
when
Lean will
you're
warn you when you're being non-computable, and you have to tell it.
Is it implemented interval arithmetic where it could be computable?
So if you really want to do, I mean, there's a type of float, and I think it's computationally there. I think we don't have any axioms about it. It's in the formal system. I think right now it's mostly non-axiomatized
Because like the stuff we're
constant.
doing next week, we would like to have interval.
Yeah, right. So I mean, what this means is, I mean, you can certainly so you can basically define any computable. You can do,
I'm sure it's possible in
Right.
principle. I was just wondering if it's there in there.
If it, in Mathlib,
Yeah.
there isn't. I think there isn't much interval arithmetic. I don't know. It may be out there in some repositories on that, but that's a project to implement interval arithmetic. Yeah. Okay. So that's the idea. So I just propose now just to do some examples of proofs. And again, maybe you're following along, maybe you're just kind of watching, and this is just performance art on my part. But I just want to just give you a feel for this. And then I'll stop talking and let you do it, and ask questions and see how it goes. But just to just to have some more interesting mathematical examples. So here's one example. So let's define the following function recursively. So let me define a function f from natural numbers to natural numbers. I'm going to define it recursively, so let me map 0 to 0, and let's map n plus 1 to 2 times n plus 1 plus f of n. Okay, so this is just adding up the first n odd numbers. If you doubt it, you can sort of evaluate f of 0, you can evaluate f of 1, you can evaluate f of 2. Okay, so we're getting 0, 1, 2. In fact, let's generate the list, the first 20 integers, and to each one of these, let's just apply f, map f. So what I did was it just generated the numbers from 0 to 19 and applied f, and that looks like it's just the first 20 squares. So we should be able to prove this as a theorem. We should be able to prove that for all n, f of n is equal to n squared. actually, let me do it done. So what's going on here? So example is just a theorem that I'm not going to bother to name. So so if you give a theorem a name, then when you're done, it kind of Lean remembers it and stores it, associates the name. Example is just good for playing around, and it just it checks your proof and then just throws it away. It turns out to be convenient when you're writing proofs to. So there's a command that says done. This says that you're done with the proof. Lean is giving you an error message saying that you're not done, you haven't proved anything yet. But the reason that this is helpful is that if you don't do it, I think often the error message ends up being, well, it's kind of all over the place. Sometimes the error message gets attached to the thing. So it's kind of a way of kind of controlling where the error message goes. Okay, but so now writing by, what the by does is it tells Lean that we're going to write this proof not by giving it an expression, but we're actually going to give it a list of instructions that's going to tell Lean how to construct an expression. So this is called a tactic proof, or we've entered tactic mode. And so the first instruction I'm going to give is to say, look, we want to prove something true is true for every n. And so let n be arbitrary. So introduce n. So for all n is arbitrary, and I could introduce I can say let m be arbitrary and prove that f of m equals m squared. So the for all n is a bound variable. It says for every thing, f of that thing is that thing squared. So let's prove this by induction. And again, don't worry about the syntax. I'm just kind of throwing these examples at you just to give you a feel for what's going on. So what's going on here is I've given it an instruction that says I want to prove this by induction, and so now you'll see the two cases, the two goals on the right. So first we have to do the zero case, and then the successor case. The zero case, you have to show that f of 0 is equal to 0 squared, and often with proofs like this, you can do it just by unfolding definitions and and just calculating the terms. So I just say that's reflexivity. And so now this is the more interesting. This is kind of an annoying bug with the induction tactic. You don't see the goal unless you're kind of on the next line. But anyhow, so now we're in the successor case. So I should have said. So what you're looking at is called a goal. And the way to read a goal is, first of all, you have a context. So this is kind of the objects and hypotheses at your disposal. So at this point in the proof, you've got a natural number n. You've got the inductive hypothesis that f of n is equal to n squared. And then after the turnstile, this is the turnstile that goes all the way back to Frege. This is how Frege noted that you're proving something. So with that data and with that hypothesis, we want to show that f of n plus 1 equals n plus 1 squared. Okay, so how can we do that? Well, so one thing we want to do is expand the definition of f. So I did that with the command called rewrite that I'll talk about more in a minute, but I've expanded the definition of f. And so now we'll go to the floor. So what do we want to do next? This proof.
Apply the inductive hypothesis.
We want to use the inductive hypothesis. Yeah. So we know that we're assuming that f of n is equal to n squared, and we want to show that 2 times n plus 1 plus f of n is equal to n plus 1 squared. So let's rewrite with the inductive hypothesis. And now we have 2 times n plus 1 plus n squared is equal to n plus 1 squared. That's just algebra. And fortunately, there's some nice automation built into Lean that will do computations like this. It's called the ring tactic. It's misnamed in a couple of ways. So first of all, it assumes commutativity. So it should really be called commutative ring. But roughly any calculation that involves addition, multiplication, constants and constant powers, it'll just kind of expand and it's just polynomial, just expand the polynomials and and prove them. The other way, it's a misnomer is that, the natural numbers aren't a ring, it's a semi-ring, but the ring tactic works for semi-rings as well. But that's it. So we have a proof. Lean gives us a little warning saying that, saying done doesn't do anything. And so we can kind of get rid of it. But now we have, now we have a proof of a theorem. I mean, if we gave it a name, let's give it a name. Yeah, then you've actually proved something, and Lean, remembers it. So, until the end of time, or until you turn off your computer, or save it or don't save it. If you ask Lean, what is f eq? Lean says that's a proof that f of n is that for every n, f of n equals n squared. That just becomes an identity that you can use, anywhere later on. So you prove and what you can do is, let's see if we print, yeah, so this is actually, all your instructions, what they did was they constructed this complicated expression here, okay, which is your proof. So often when you use automation like ring, things become very verbose because it's moving things around and putting things in normal form and so on. But what you've done is these instructions have been instructions to Lean to construct that expression, and really f eq is associated with that expression, which is a proof for all n f of n equals n squared. Yes.
Is there a way to save the underlying Lean proof? Like right now, something like ring or even rewrite maybe depends on some implementation of these tactics, but presumably, it has applied like a bunch of axioms. Is there a way to sort of save that or extract that?
Yeah, well, so a better question is what you can do with it. So it is there. It is buried in the bowels of the computer. It's there, if you so when you if I were to build another file that if I were to write another file that depends on this, Lean would compile this and store a compiled version. So we have a binary file with the representation of all these objects. So they're there. The question is, what do you want to do with these objects? So that's what. So when you load Mathlib, for example, it gives you all the source files so you can see them, but it's also loading all the pre-compiled expressions. They're there on your computer.
But not particularly accessible to the user.
So they're not meant to be accessible to the user. Yeah. So and this is an interesting point. I mean, this is something to talk about. That where is the actual information? So very often, I mean, for example, you'll use automation like ring, and it says, yeah, I did it, right? And, very often you'll use automation. You want to know, well, tell me the proof. What's it look like? And a priori, you don't have to write automation to make it accessible. But then there are questions like, well, what if you do want more information? So then there's more to talk about. But by default, a proof is a proof, and it's just this data structure that's somewhere.
Especially some of them are something very complicated. If you try to look at what happened inside, they write everything on normal form on left and right, and then try to say it's the same thing. So it's not something you will do on a paper.
Yeah, it's not right. It's not something that.
I mean, I remember I tried once to. I mean, maybe you don't want to hear that. I tried once to modify ring to see what was inside, and that's a terrible one.
But just as I barely use this, but I know like this rewrite tactic is using two things, but if I wanted, for example, just see what the goal was after the first one, I'm not sure how to do that without breaking into two lines. After the F, like for example, what's the goal after F? You just move.
Oh yeah, sorry. It shows it's actually as you move through.
That's all great.
Yeah.
But it must have been a choice. Is there just some way of having it write as comments what the goals are? So you can, I know you're used to doing this interactively, but it was just on a piece of paper. Wouldn't it be nice to sort of see non-interactively?
So there is the Lean FRO is developing tooling so that you can generate HTML pages that have exactly this, but as you hover over it with your cursor, you can see and so on. Also, let me say that as far as machine learning is concerned, I mean, if you want to teach machine learning, the question is what are they going to learn from it? Typically, you do the training on the source files rather than the proof terms. But also very often what you want to do is, there's more information in the proof terms. And so, there are methods where you can take the source files and kind of augment them with more information about the state and about the proof terms and so on. Show those to language models and let them train on those. So it's almost a philosophical question is, when you have a proof, what's the information you want? What is the information that really conveys understanding?
And that's the stuff that this lead dojo, and I understood the alpha proof was also using, in your case, you were using like a language model to look at the goals. And
the goals and the tactics, but not the proof term.
Yeah. Which is a very sensible thing to do, because again, this is, what we're doing when we look at these, we're looking at the goals and we're writing tactics. So it's the same information that we would see.
So what's the difference between ring, ESOP, and SIMP?
Just different automation. So they just do different things. So the ring does calculations in the commutative ring or semi-rings, which is polynomial multiplying things through. It's good for things like that. Simplifier is generally equational reasoning, and it's meant to just take complicated expressions. And so over time, as you develop the library, you just keep declaring more and more identities. You tell it x plus 0, just always simplify that to x and so on. But it actually turns out to be fairly powerful. I mean, you can actually throw a lot into the simplifier. So
let me throw, there's this kind of general question, is this, it's clearly not the way mathematicians naturally think, but you can learn it. And so you kind of maybe think lean should become somewhat more like the way mathematicians think, but that you already think. But then it could also be that many of these distinctions are useful ones that people should start to appreciate. So like, would you say that the difference between RW and ring and set is something which a mathematician should have actually been aware of? Or is it like something that just lean has to know, but the mathematician should not have had to have been aware of?
So I tend to think that from the point of view of formalization, what we really want to do is have declarative proofs where you say, we basically, so I'll show you have statements in a moment, but basically where you can say you have this, and then you have this, and then you have that.
Right.
I think the idea would be to be able to write proofs at the same level of detail that you would write a mathematical proof.
Okay, so let's come back after.
And then have everything in the middle be just by some kind of automation.
Okay, well, I can ask some other version of my question, but I'll wait till you do have some more stuff.
But I also think that this is also, so I should say that, automation for lean is coming online as well. But I think this is also roughly going to be good for machine learning. I mean, what we want machine learning, what we want to do is have examples of proofs that are structured that way. And Isabel was very good for this. Isabel was a great system because the methodology, they relied on automation a lot. The method of writing proofs is very structured proof and just trying to prove everything in between with automation. And I think that's good for language models. I mean, the automation does the symbolic things that symbolic proof is.
I mean, but just to give a little more substance to my question, I can imagine making the case that, well, yeah, if you look at the way a person really works on paper, sometimes they cross out and put this thing there, and that would correspond to RW. Sometimes they reason in a different way, and that would correspond. So it's not impossible that these distinctions that we tend to slough over.
Yeah, I mean, there's structural thing. Well, certainly by proof by induction. That's a proof move. That's right. There's also a calculational mode where you start writing, A is equal to B, less than equal to C, and so on. And then there are a lot of things well, that's just obvious, which turn into called linearith, called rough, or just kind of write this long inscrutable string, which is kind of hacking through. Yeah. Okay. So far so good. So in Theorem Proving, we just go through examples. I propose I'll do this for another 10 or 15 minutes. So one of the things that, one of the first things we do is, we teach you how to use the rewrite tactic. And one of the design decisions in, writing mathematics in lean is that we try to make the examples interesting mathematics. So very quickly sort of establish, even though you're just using the most basic, you use the most basic commands, you're actually proving real theorems. So here's a theorem that if G is any group and has the property that for every x in G, x times x is equal to 1. Okay, so every element is over at most 2. Then the group is abelian, right? So for every y in Z, y times Z is equal to Z times y. And that's a homework exercise, right? For your abstract algebra. And so it's a great thing to be able to do in Lean. There are a couple of proofs here, but one way to do it is just be clever. You write y times z is equal to y times y times z times y times z times z. And you write z times y equal to that same thing. So if you can prove they're both, then they're equal to each other. Right? So the sorry is just a placeholder. It says that, I haven't proved it yet, just leave me alone. And, Lean tells you that everything is fine except you haven't proved it and knows that you've used sorry. But once we have H1 and H2, we can prove the final goal just by, if you rewrite with H1, right, then you're replacing, the thing on the left with the identity. And then I can rewrite with H2 either backwards or forwards. So if I rewrite with H2, then both sides look the same, right? And then Lean figures it out. So okay, so opening to the floor. Why does the first equation hold?
Do some associativity.
Yeah, so we have, we have the axiom that, x times x is equal to 1. So y times z, that y times z times y times z in the middle, that should reduce to 1. But now you need to know that the parentheses associate to the left. And this is actually a kind of a criticism, though. In mathematics and Lean, we start off with examples of kind of associativity and moving parentheses around. And people worry that, to most mathematicians, associativity isn't even something you ever say, right? I mean, what do you mean you have to prove that x times y times z is equal to x times y times z? So but yeah, so we do have to move the parentheses around. Let's see if we rewrite with mul.
But that was an example of something where the person should have known about that concept.
That mathematicians should, well, because there are non-associative.
Exactly.
Let's see. No, I think maybe we should. Hold on. So let's think about what's going on. I have my cheat sheet here, but so this is y times z. Yeah, so it's the parentheses by default associate to the left. So I think I want to do rewrite with maybe mul. So y. It's kind of this game. It becomes this game of how you, how you give it enough information to apply the right.
But there is this meta principle of just, once you grant associativity, you could have in some sense drop the parentheses, right? So why not implement that?
So there is automation that will do better, but we're just doing it by hand. So what I've done is I've kind of moved the parentheses over on the right, and now the thing in between the outer parentheses is of the form x times x, right? It's y times z times y times z. So if I rewrite with h, that becomes 1. And now you need to know that there's an identity for any group that says y times 1 is equal to y. Names in Lean are chosen to make it easy to guess. So the axiom says something about multiplying by 1, and so the identity says mul 1. And now I'm getting an error message on the sorry saying, you shouldn't be sorry because, there are no goals to be solved to prove that. Okay, and now looking at the second one, why does the second identity hold?
H2.
Yes.
H2, yeah, why does H2 hold?
If you associate the y squared and z squared.
Yeah, if you move things around, you should be able to get the y squared on the inside and then the z squared on the outside, and then they go away, should go away. All right, so now we just got to figure out how to do that. So let's see. I'm just going to cheat and figure out. So what I'm doing when I say do mul, so with associativity, put it down here just to make the error message go over there. So when you say do associativity, if I just say mul assoc, Lean will find the first instance of associativity it can. And if that's not the right one, you can give more information to mul assoc. You can give it exactly the arguments you want it to use. In this case, just giving it the first one is that enough to do it? No, wait, what? Oh no, I'm looking at the wrong one. Oh, yeah, according to my notes, if we do associativity, that one, so what did that do? Yeah, oh, the y times z. Okay, so now with the y times, let's see if we can make the z go away. So this is y times z, but we say let's give the y and the z. So now we got the z times z, and we can rewrite that to 1, and mul 1 will make that go away. And now how do we get, oh, these pop-ups will drive you crazy. Now you want to get the y times y together. So I think doing mul associativity the other way. So let's write associativity backwards. I'm sorry. Mul assoc. We'll probably do the wrong one. No, that looks right. Okay, and that was probably h. Yeah, and that became 1. And then, yeah, so what's the final theorem? I want to rewrite 1 times z to z. Mul 1. So no, sorry, so not mul 1.
Oh,
Yeah,
sorry.
One.
One mul.
One mul.
There you go. That's it.
I guess you're saying one mul, one back.
Then you found.
Yeah, then they did. Okay. And so that's the game. Yeah. By the way, I don't know if I've duplicated. So we have a first order theorem prover, proof producing that will prove this automatically. So again, the goal is to get more and more automation. But yeah, the goal of the first section in mathematics and lean is to teach you how to use rewrite. And so, yeah, now you know how to use rewrite.
That kind of manipulation, is that not in like sim or lineareth or?
So simp, what you can do is simp, you can rewrite. It's good at sort of moving all the parentheses to the left and moving all the parentheses to the right. You can also, if you give simp commutativity, simplifying with commutativity sounds dangerous, right? Because you can just keep rewriting, right? But lean does something clever. It detects that you have a permutative, like a rewrite rule that's just going to keep looping. And so what it does is it only applies it if something goes down. There's some arbitrary ordering of terms. And that has the net effect that if you simplify 2 expressions, that are equivalent up to associativity and commutativity, and there's another aspect called left commutativity, you can get the simplifier to prove things equal just by moving the parentheses and switching terms in the right way. But
how does one give sim like extra hypotheses? Like, are we able to like give sim h, for example?
You can do, so this says simplify with that whole list. Yeah, we'll come back to the simplify.
Okay.
Yeah.
The rewrite applies equally. It doesn't care whether it's on the left or right, and the equals, it just.
Yeah, anywhere. So it doesn't even have to be an equality. It could be any statement. It could be a divisibility statement. It could be statement about contiguous functions. It does not go under binders. So if you have a summation or a quantifier, you can't rewrite under a binder. But otherwise, any expression will just find the first thing that matches, and it just rewrites it. Okay. So let's do maybe just one more. So after rewrite. Look, of all the things in mathematics, equality comes up a lot. So being able to do equational reasoning and calculate is important. So that's why we start with rewrite. But after that, the next thing that we showed in mathematics is just how to apply theorems. Maybe let me just give you one example of that, and maybe even 2 examples. Oh, there was another. I deleted it. Okay, let me. So let's do let's do some modular arithmetic. So this notation on line 116, it says that A1 is congruent to A2 modulo n. So the syntax is if you hover, how do you get it? It's /==. It's just kind of lean syntax, but so the Z mod is there's a notation for the natural numbers as well. And this is what makes it specifically integer arithmetic. But so all the variables are declared to be variables of integer type, and this says that that n divides A1 minus A2. And so we're being asked to prove that given that A1 is congruent to A2 and B1 is congruent to B2 and C1 congruent to C2, we want to show that A1 times B1 plus C1 is congruent to A2 times C2 B2 plus C2. But we have some facts in the library that we can use. Let's sort of run through them. So first of all, this is what the notation stands for. It's called int.modeq, and there are 3 arguments, n, a, b, and it's a proposition. It says that a is congruent to b modulo n. And we have one fact, we once ported, I think it doesn't even, we don't even need the at signs. Let me get rid of them. So we have one fact that, A is always congruent to A modulo N. We know that if A is congruent to B, then B is congruent to A. We know that if A is congruent to B and B is congruent to C, then A is congruent to C. We know that if A is congruent to B and C is congruent to D, then A plus C is congruent to B plus D. And then there's one, so this is just a special case of addition where you fix one of them. So if A is congruent to B, then C plus A is congruent to C plus B. So there are other facts. So for example, there's an add right. There's also there are facts about multiplication. And so the next tactic to tell you about, if you don't know about it, is the apply tactic. And what the apply tactic does is it has the effect of reasoning backwards. If you're trying to prove, so one way So one way to read this theorem is, as a rule, it says if you're trying to prove A plus C congruent to B plus D, one way to do it is to show that A is congruent to B and C is congruent to D. Okay, so you can read theorems going forwards, but you can also read them going backwards to show the conclusion. It suffices to show the hypotheses. And the apply tactic does exactly that. So given a goal of this form, if you say apply this theorem, it says, okay, your task is reduced to, proving the two hypotheses. So my question to you is, at this state in our proof, given the goal, so the order of operations is, what you would expect. So multiplication takes precedence over addition. So my question to you is, in this state, so given those objects and those hypotheses, HA, HB, and HC, what's the theorem that we want to apply to the goal to make progress?
Just applying all the hypotheses of equality.
Well, so we want to work backwards. We want a rule that will give us this as a conclusion. And so we want a rule that will tell us, so they're not equations. They're not equations, right? It's congruence modulo, so you don't have a substitution rule.
Right.
Okay, so we need to use these theorems, right? And that's why we have theorems that will let us kind of break it down step by step. Anyone else?
Well, C1's congruent to C2, so okay, is there a way of saying it equals?
So we want to reason backwards.
Yeah.
We want a theorem that will enable us to.
Was that add right? I don't know.
Well, so let's try it.
no.
Let's apply. So let's say
Oh,
apply.
I'm not sure what it's going.
What? So let's try it. Apply int.mod peak dot add right. Right, and you get an error message. So what the apply tactic tried to do is it tried to interpret this as a pattern. A plus C is equal to B plus C, and it just couldn't make it back.
We have to give it more parameters. We have to tell it.
No, so if you look at it, so the problem is, for this to work, the question mark A should be A1 times B1, and question mark B should be A2 times B2, but then question mark C, well, on the left, it's supposed to, match with C1, and on the right, it's supposed to be C2.
In the word.
So what?
No, sorry.
Did they have handle the case where they both were constant?
Yeah, so we did have one, yeah, right, so that was, the add was the more general one.
Just the general.
Yeah. So let's do the more general one. There we go. And now Lean did succeed in matching the conclusion. And then when it matched the conclusion and applied the theorem.
It's because the general one is not assuming that the guy on the left is. equal to
Yeah,
one.
so the add one does both at once, and the left and the right does only one at a time. Okay. Good. Okay. And so now we're faced with the goal of showing that A1 times B1 is coming to A2 times B2. And that's not one of the theorems listed above, but now I'm gonna ask you to guess what the name of the theorem should
Can you
be.
rewrite it?
No.
Times.
Can you rewrite with HB?
So we don't want to use rewrite because there's no equations here, but we want to apply.
Is there mo? I don't know.
Yeah.
Can you say more about what you mean that there are no equations? I mean,
Oh.
to me, those are, qualities of elements. in
Yeah,
the-
no, so this is really just a
C mod n?
three-place there, well, you're thinking of it of equality modulo n, but equality modulo, I mean, this is defined to be n divides a1 minus a2. I mean, it's
I see.
it's equality modulo n.
So those A's are integers, not elements of Z mod n?
Exactly. There are three integers there, there's a1, a2. and
Can I work with
You can,
elements of
you
the
can,
ring
you
Z
can.
mod n?
So we can go,
Okay.
so so the.
Okay, but this is
Um,
just not the setting in which you work with elements of
So
the ring
let's,
Z
let's
mod
see if
n.
this actually, if I put it, Z mod n, Z. So we have the data type, and, oh, wait, oh, but Z mod n is, so, wants m to be a natural number. Okay, so there it is. So yeah, so we do have the integers modulo m, and
Okay,
so one option, and there are theorems that will translate, congruence equations to equality in a range, in the ring calculations.
Because this is, you're working on a module here, it's not in C mod n, some of these guys.
No, this is just a elementary number theory. This is when, this is number theory 101, where this really means that n divides,
It just was,
so so the first one means that n, well, the goal means that n divides the difference between the left and the right side.
mhm.
So that's why we're using apply instead of rewrite. We're applying theorems that will let us do that.
Okay, so it was some theorem like if n divides x and n divides y, and then it divides x plus y.
Yeah, exactly. So in fact, we're going to use a theorem that says that if A1 is congruent to A2 modulo n and B1 is going to be then product. And so it's going to be, int mod eq dot mul. There we go. And now we have to show that A1 is congruent to A2, but that's just an assumption. I can do that by saying apply H1, so HA. And then the next goal was B1 congruent to B2, but that was HB. And the last one is that C1 is congruent to C2, and that's apply HC. And then we're done. Okay. And just to look at the expression, let's call this theorem. The problem is, keep running out of names. Here we go. So print through that one. And it really is actually it's kind of almost readable. It's basically you're taking the add of the mul. So you're taking the property of, you're applying mul to HA and HB, and you're applying the add axiom to HC. So the expression that describes the proof, is kind of a reasonable description of the proof. But again, conceptually, what you're doing is you're just applying theorems and working backwards too. So in other words, applying this first theorem, reduces this goal to goals that are easier. And then when you're the plan is you keep doing that until you get to a goal that's trivial or straightforward to prove.
Could you go back to that expansion with the print? Does that mean that I could have typed that in if I was smart enough?
Yeah, let's try it. So, let's see. Let's comment that out. So when you're giving a proof term, by yourself, try it again, print through. What it is going to do. Should copy it. No, file. Let's copy. See if that works. Ooh. Yeah, I do. Wait, no, sorry, X. Wait a second, what did I do? Oh, no, okay. I made a mess of things. So I deleted the proof, and the answer is yes. So you can give the expression. Oh, and in fact, see if we can make this. So there is a way to do it automatically to show term. Yeah, so you can write a tactic that shows it. And then if you click on this, you can actually get it to insert the thing in five for you. Okay. So, this is a good starting point. So again, if you've never tried Lean before, this is a good time to just start with mathematics and just kind of work through. And I'll stick around and answer questions.
This is a basic question. How do I search for theorems? I mean, besides for the name.
Yeah, okay, so good. So it's that's another kind of long story. I'll give you, there are lots of ways. The best way and really the most effective is to, if you can guess the name of the theorem, if you can start to guess the name of the theorem, tab completion pops up. And so let's, right, so if, so let's, so if you start int, so apply, so int dot body, okay, and now things start coming up. Left, F cancel. So if you can, if you can start guessing the name, and theorems are named, so there's a methodology for naming theorems that makes it easy to guess. There's another tactic. Let me comment this out for a moment. So the applied tactic comes with a version where you can just say, give me a list of things I can apply. And a little bit of search. So the yellow bars need, Lean is thinking and processing. And yeah, look, it came up with, it said, try this one. It was exactly the ModiCAD. And so, so what it does is it goes through the library and looks for things that will match. And then there's kind of a heuristic ordering. It tries to give you the most, the most likely useful matches first. There's similarly a rewrite question mark. There's also a search engine. How does it work? I can't even remember.
Google.
Yeah, there's Moogle and Lugal. They're online search engine. There's actually one in the browser. Let me try to fiddle with it afterwards. But there are also ways to search symbolically. There are also engines driven by large language models where you just give it just a verbal description of what you're looking for, and it'll try to find something relevant in the library. So.
Moogle is just some tool.
Yeah, Moogle.ai.
Oh,
Just type in yeah.
How do you spell it? M-O-O?
I mean,
Moogle?
it looks like Google.
Oh,
Yeah.
Moogle. I see.
Let's say adding to congruent numbers, gives a congruence or something like that.
The documentation is nicely made as well.
Oh,
Add congruence, add con.
Fields of mathematics was very much.
Okay, so that didn't help. Congruent numbers, modulo. So if you're putting the word modulo, helps modulo some other number.
It's called the API documentation.
There we go. So just typing in. That was pretty good. There's another one I like called lead search.
Well, this one, for instance, is easy to type into Modec and see all the theorems of Modec.
this one is what? This is the Moogle?
No, this is just the basic documentation.
Oh, basic documentation.
Move them to there.
Yeah, yeah. So another thing, right? So there is the basic documentation. Community. So here, if you go to the API documentation, there is both. I mean, if int.modic, you can sort of do search by the identifier. You can also do a Google search. Let me try to remember how to do the Google search. There we go, lead for Google search. There we go, we can get a window. And so this will, yeah, let's see. So if let's see if I can do this. So if we want, the theorem we wanted was something plus something is congruent. Something, plus something, mod something. And, oh no, it didn't like that.
Z-mod is capital.
Gmod, yeah, okay. Yeah, came up right away. So yeah, so there are basically symbolic search engines and there are machine learning based search engines. But really the idea would be to just not have to find them at all. But really just say, just do this automatically. And that's really the goal, with a combination of kind of symbolic automation and machine learning automation. We'd really like to say, come on, this is just obvious, just do that. Shall we stop here?
What's surprising is that between the search engines and these searches and the tactics, it's smarter than me. I don't see why I have to do it. I mean, it must be so close.
You would think that, yeah. Oh, another thing is, so another thing you can do is turn on Copilot, GitHub Copilot. If you have an education, if you have a .edu address, it's free. And Copilot does well. I usually turn it off for demos like this because, again, Copilot will remember the last few files that you've opened. So, to prepare this, I prepared a file with all the answers filled in and so on. So if I had Copilot on, it would just keep filling in. It would just remember the proof that I gave it, that it saw yesterday and keep filling it in. But yeah, GitHub Copilot is quite a good tool as well. Okay. Thank you.
We're going to try to put some of these proofs ourselves.
Yeah.
Do you think it's realistic to tomorrow morning to kind of go through and help people sort of a little project or proofs, or should we
So the question is, again, there's a lot to learn. So if you're just learning to do rewrite and apply and so on, maybe let's wait another day to let people explore Lean a little bit more and so on. At least maybe on Thursday, they'll define computers, at least formalize statements. Yeah. I'll get some. I'm just gonna go get some water, but I'll come back and just put up a hand and I'll come back.
Thanks so much. It's really great. Thank you.
Yeah.
So I usually when I go to Google, just in Google, I move. Sorry, for what? Sorry. How do I bring up Google or Google? Like, just in Google for Windows. There's nothing to do with me.
Oh, I think so. I haven't used Google.
It's Google.ai.
Oh, that. I'm sorry. It's just on the internet. It's nothing to do with the.
Oh yeah.
Oh, okay. Yeah, Google.ai. It's weird. Let me see log out there. That's right. Yeah. Vincent here.
Okay.
I'm Vincent.
Oh, Emory. I think I can afford do that. Import method dot maybe data dot net. Maybe just try that. I was just gonna say that.
French, it would not be without studying.
Maybe.
AI.
Yeah, I'm getting this real thing, we're waiting about connection is private, I don't know what this is before. Yeah, it's really, I mean, I could do other things. See. Yeah, it doesn't, that one doesn't work. I think I'm doing like a Harvard guest.
So you can
You're like the other guest?
No, I'm working on the Theorem.
Say again?
I'm working on the Theorem.
Oh,
Yeah, I can make,
I don't have that. Yeah. Come on, look.
you remember the S? You put on this and remove the S at the end of each CBS?
Oh, I see. Can I do this? I see. I don't like
Yes, I'm trying to show, yeah, so I told you that it's putting this kind of project as well. So, yeah, a bit more context, yeah, so this is the theorem.
No, it's okay.
That, yes.
It's-
And this is like a textbook solution.
Okay.
And I'm trying to prove it.
Okay, great.
So like, I mean, I've got some of the idea. This is really silly thing that I feel like. So this is my state. Like I have this integer, well, this natural number m, which is defined to be n minus 2, and n is some other natural number. And I know I have this hypothesis that it's at least 5.
Okay.
And so I want to prove that n is at least 3.
Okay.
And I thought that should just be simple, just by a simple limit or something. But like that didn't work.
So try omega instead of omega.
Omega.
Sorry?
What is it? I've not seen it.
So omega, so linearith does is for linear arithmetic. So it's really good for linear arithmetic kind of problems on the reals. It doesn't handle kind of discreteness. So it uses heuristics. So like if they're given, n less than n, it will rewrite it to n plus 1 less than or equal to n. So for the integers, it treats them as real numbers, but but it's not complete in any way for things like that. Omega is basically linear integer. It's a tactic designed specifically for linear integer arithmetic.
Okay.
Even in principle, we'll do simple divisibility problems.
Okay.
But yeah, this is the canonical use for it.
Okay. So now, like one of the more maybe difficult steps I'm trying to do. So in this proof, so as I said yesterday, it's working in this number field, and well, specifically in the ring of integers of it. So the ring of integers for this number field is z square brackets this element 1 plus root 2. I want to put this expression. So I want to tell Lee that like 2. If you think
They'll have to cast it, yeah.
If you think of 2 as an element of the ring of integers, then its factorization into prime elements is this.
Okay.
That's what. So I asked Copilot. So I wrote a prompt.
Let's see. So does it know anything? So we divided by what we divided by? It's this is the field.
This is what I thought it was.
Oh, I see. Okay. Okay, so.
And then, so it gave me certain reports that just didn't work, and then it's asking me to prove the theorem that two kind of splits in this way.
Yeah. So does it know that? I mean, does it know? I'm trying to think. Where's this calculation happening? So there's the ring of integers. There's the number here, but does it know? So notice that this is
Well,
embedded in that.
that's not even the ring of integers. So that's actually like an
Oh,
order.
yeah, yeah.
That's like an order in.
Yeah.
That's not the
yeah,
maximum
yeah,
order.
Yeah. So what exactly is going on? So ring of integers is known to do that.
That, I guess that's like a theorem, like undergraduate algebraic number theory.
Another question is, does Lee know that?
Yeah, so I think these things are defined somewhere in the number theory as well. Yes, it's z square root d. There's a whole like module for this. Yeah. The ring of integers joined with the square root.
Yeah, but that is just integers are joined with the square root is not what you want. You want something bigger. You want the ring of integers are joined with.
Yeah,
That
1 plus 2 minus 7 over 2, yeah.
Yeah.
I mean, if there's statements about a class number and like it being finite, like this has to be kind of somewhere, I guess.
Yeah, well, it's defined the ring of integers and each according to zoom in our field.
So I guess I want to define the number field and then its ring of integers and then pass 2 into it. I guess these might be like the first steps.
So again, this is really this is impressive. So you can say. So this is a number field. So here's the number field, and here's my ring of integers. But then
I don't know what I did.
at some point, you have to calculate, you have to get convinced me that.
You were Googling before?
It is what you think it is.
That's
Yeah,
for
that-
3 hours.
Okay, I can put a story in that now. But like that
Yeah,
was
but I
I literally
so I
just
guess I don't
found
even
out
know how to
about
say
that
that.
yesterday.
Right.
What's the other thing?
Delicate. That I see it. Right, have you told before?
Sorry?
Yeah,
Yeah.
they seem to be
I
general
was
things
looking
about
through the.
like number
I did
fields of
some in
arbitrary.
3 last,
of
but I have only 3
arbitrary
hours in E4.
Okay.
But this thing about
You know,
like
there are many things that-
quadratic number
Right,
fields are like a specific thing, which is like what we're working with.
You
So
I used
I'm
to back
working
on
with that.
before, I see, okay. No, I realized, I mean, I just literally started to do it
This is a good question to ask.
So now I'm learning.
Because there are people, I mean.
The differences between
we've been a lot of.
Yeah, there are differences. There are lots, many differences where you have to say letters and lowercase.
How do I write?
You go to them.
And
trying
how
to
do I
look many differences.
how do I convince
yeah.
you of this?
And,
Yeah, but even to say that.
you have
one
to, for
of the- one
example,
of
the
the
way you
calculation
place your ears, the
ring
way
of
you
integers.
So right now,
That's
it's
even
weird,
knowing
like,
that
that's
ring
right.
is an integral.
Yeah.
And it,
I
and
know,
it's
like,
like, I
I
don't
think
even
that
know how
is,
to.
like,
you know,
any of these
write
assistants,
that. So
are
ring
not
of
so
integers
great
is-
until you
is-
need
is-
reasons.
is-
I mean, if you have like Gemini or something.
I mean, in general, you can't
of
just
course
say,
they-
well, it's
they don't know
1
that.
plus square root of negative 7.
So now ChatGPT is better in E4. And Font is actually.
I don't even know.
Oh,
Yeah,
fine.
but-
Okay, that's not good.
Alright, okay.
Well,
So,
it's
I
just
think
that,
that's- that's a really good
it's doing
question.
just like the previous version of ChatGPT,
I
because
see.
speaking online sometimes. so
I
it's,
see.
Well, you have to say in E4, otherwise.
Yeah, yeah, yeah.
Otherwise, it still brings back an excuse.
Yeah.
Has a completely different.
Yeah, because then it goes on to say, so
Here,
I already have this
I was looking
place
at something
somewhere
because-
on my stage.
Okay, there's
And then I went
some
back to our
small
website to get
difference
this.
in,
And
between three and
I've
four,
also
the
explained
number
yesterday, and then
you
there's
have
this
the
idea that
digits of
these
the
are
number.
prime.
And
so
in three,
basically
it gives
one
you
of
some
these two.
numbers,
Okay.
right? Because
Yeah,
you want
that's
digits
good.
of 1 and 1,
See
which
what
is
it
sensitive.
make you get back.
And then 1,
I
you
mean,
do
there
1
there
and
are
1.
headaches of going.
And
from
in
integers,
E4, you
you've
do
got
your
between-
characters, not natural
Oh,
numbers.
really?
So I was wondering, okay, how do I do? And so I was saying, okay, how do I do, is there a function for
Yeah,
there
going
is a
back to
function,
fields
cars
and
to
rings,
nuts,
yeah, there are
just to nuts,
headaches
number,
involved.
there's also cars to nuts.
Yeah,
go back in the other direction.
I've actually been
Now I was
struggling with
telling
that
it,
just between like
okay, now I
the
have,
integers and the natural numbers.
Yeah.
That,
function
like,
that is
certain
a list of
things,
characters,
I
and
wanted-
wanted natural number.
I wanted this thing to be like for all, like,
It's
for
only
all
in the
n
end, like,
integers as well.
Yeah,
But
so
that was
this-
proven to be too
Oh,
too pain.
yeah,
So
I
that
I just added these
the
and
natural
put
stuff.
Oh, very good.
Oh, I see.
So what have
Um,
you formalized in the?
Oh, I see.
It's actually true also for like if n is like n is negative, well then I guess this is not gonna have any solutions at all. Just because like that's gonna be less than one and that's gonna be just by size there.
Yeah.
Here's the problem. This thing
But
here,
like, I think you can tell the way you want to do it is just start with this.
Yes.
So in base 10,
Yeah.
this thing
Because,
used to be
right, because
integers.
I don't
Now
know
so it's
how it
characters.
works.
So you
Oh,
can use
yes.
characters.
So you gotta do
So
some.
I need to do exactly the same.
Okay, well yeah.
Yeah,
I'll also do it.
yeah.
This.
Yeah, do that. Let them have this.
Okay.
Those. And then it says I don't remember, but before I managed to do the keyboard. Maybe it's not exactly. Yeah, well, I think I did somewhere else because I too. Yeah, that's this one. That's the How about this one? So go to this one.
Oh, that's nice.
And then
Oh, very nice. Oh, I love this window. It's telling me some good stuff here.
Thank you.
So I followed your instructions about here, what should I do?
Oh, so what do you want to do? You want to specify that you want to do it with one of the ones where. you wanna do
Can I apply this here y star z times y star z because y star z can be considered as x? Is it possible?
Yeah.
Then how can I apply it?
Yeah, so let's think about it. So this thing on the right is y times z. And it's really, putting in the extra parentheses, when there are no parentheses, the parentheses are to the left.
Ah, I see.
Yeah.
Ah, okay.
Okay.
Sorry.
Okay, so what you want to do is you want to go from that
you use the hub
to, y times z times y times z.
Right.
You want to go from this to that.
Yeah,
And that's using associativity,
yeah.
Mollisok with y is the first argument, and that's a, that's b. And you want to use the identity that says that a times b times c is equal to a times b. Right, so you want to use this identity where a is y and b is y times z and c is y times z.
Right.
And so, so the full way to say it is you can say use Mollisok y times z, Right, if you say, rewrite with that, that'll give you exactly the one you want.
Oh,
And then the trick is sometimes you don't even need that. Like, so if you just do that, it will find the first instance of associativity, where y is the first one. And if that happens to be the one that works. So,
I see.
yeah, the
So I
trick is,
just
so you don't want to say at y. That's
like this.
yeah. Yeah, that looks like
What
it
happened
did
to
it.
that? I broke my thumb. Oh,
So there is there's a parenthesis. I see. Then I
What's
can
what
apply.
you were trying to catch the ball in it, like
Or
save the ball.
can rewrite it.
Yeah.
On the top.
There you go.
And
Ah.
yeah, that's broken.
I thought that I have to
Yeah, it doesn't come off.
remind. I have to remember that there are hidden
Surgery
parentheses.
second time.
Yeah.
Thank you.
It's painful,
Ah,
right?
Yeah,
that
it's
part.
definitely like just
Once you get
but
used
it's
to it,
kind
it's,
of annoying. I haven't
Okay, thank you.
Sure.
More of a curiosity.
Yeah,
So the first thing which
I'm gonna
came
use
to
this
mind
excuse to see if
Gödel's
the voice
theorem.
interface is
Yeah,
any good.
but
See what happens.
I had a quick Google
Yes,
search, but
chatbot,
it says
so
there seems to be no implementation.
That doesn't work in a group
I was
setting
just
very
curious.
much.
so you want the first two
First,
So
second,
4 weeks
what was
until
it?
the
Non-expert.
after which time I
basically
hope they'll put on
there
kind of removable cast.
This
rather than
guy's
fixed ones. Yeah, I can type with the default thing is if I rest it at this angle. I think that's too short to try and learn
That's
left-handed
still recording.
key
Let me,
bindings.
Yeah, maybe,
Michael, I'm gonna, the Zoom meeting, is that?
unless you plan to do regular
Yeah.
work from again, which I.
I really don't.